Welcome back to ECE 340. We are closing in on spring break, which means we're closing in on our second exam. Our second exam is a week from Thursday, and you will have 2 homework assignments due before that time. Hopefully you already have most of the material available to work homework for. Some of you have already completed that, but that's due Thursday. And homework 5, which has just now been made available, is due a week from today. And that's going to be on some more Laplace transforms, but in particular Bode plots. And I want to make sure that we're all comfortable with Bode plots. And for that purpose, today what I want to do is try to motivate Bode plots, discuss what we mean when we say we have a transfer function in time constant form or it's in pole zero form, and then we'll look at it plotting individual factors and then putting all of that together to create the entire Bode plot. And we'll be doing this mainly as straight line sketches to allow us to essentially check our work if we're plugging this into MATLAB. You'll be using MATLAB to probably generate your Bode plots in reality, and what you'll want to do is just have some cues or ideas as to what you think the shape of the magnitude and phase plot need to look like, and that's what we want to try to get comfortable developing that insight with this quick sketching approach that we'll talk about today. Let's start then by reminding ourselves what we are working with. Again, we can always go back to these block diagrams. H of S is some system which is typically referred to as the transfer function between the input X of S and the output Y of S. And H of S in this class a lot of times is coming from a given circuit, but it could be coming from a mechanical system, an electromechanical system, a thermal system, an optical system. You might have some H of S that you're interested in, and we want to know how does it respond to particular waveforms, and in particular now what we're interested in is can we quickly get a feel for what the output's going to do in the sinusoidal steady state if X is made up of a combination of sines. H of S then could come from a circuit, and you now have experience with particular analysis techniques in the S-plane. Let's say that we now have a circuit that looks like the following. We now have, let's say, R sub 1, and now we're doing it in the S-plane. There's 1 over SC sub 1, and what is that right now? If I just worried about what was coming off the voltage across that capacitor, what would you now say you have? You have a low-pass filter. Now let's suppose that we cascade another similar sub-circuit on that, another RC section, and you would anticipate that this is going to be some low-pass filtering behavior. And what we want to be able to do is answer the following question. What will happen at Y of t when X of t when X of t is applied to the circuit? And then I have to basically tell you what is X of t. Well, what if this is now x of t? This is now our input waveform, and we want to now pass this signal through the circuit that I had just sketched. And what can you tell me is going to happen? Or what can you say? Or can you say anything? The capacitors are going to charge up, and now I guess I should maybe tell you this is, let's say, going on forever. And now we might be expecting a steady state response, right? But the answer really is going to be it depends. It depends on what those R's and C values are and how they then pass the different content in this waveform. In fact, this waveform is made up of 3 different harmonics of a cosine waveform, and I just put that together before class, actually about right when class was beginning. I hope now, at this point in the semester, we know what's going to happen if we were to apply, for example, if x of t was a cosine omega 1t plus theta 1, if that's now applied to h of s, where h of s is a linear system, a linear system's transfer function, what's the expression that we now know is going to result in the sinusoidal steady state output? Can you write that down now in terms of the waveform x and the transfer function h? We have where we started. We start with an amplitude of A. That's the input amplitude. And now this system is going to adjust that. It may amplify it. It may attenuate it. And what influences whether it's amplified or attenuated? What about H is important at this point? We need the magnitude of H, but where do we want that magnitude? At the appropriate frequency, which in this case is the frequency of our input signal, omega sub 1. Say, okay, we're going to get a cosine out. If I'm shaking this system with a cosine waveform, I'm going to get a cosine out, and in the steady state, it's going to be shaking at exactly the same frequency. And that particular system then may adjust the time location of the output relative to the input waveform, and that's incorporated by this phase shift, or what's the angle of this complex number h when s is replaced with j omega 1. And you might be visualizing this complex s-plane and where this particular point omega 1 is on the j omega axis if you wanted to do it graphically. But this is now telling us that we need the magnitude and the phase of h of s, and we know precisely where we need that information. We need it at the particular frequency omega sub 1. And we can generalize this. If now, instead of just that simple x of t, if x of t now is made up of many different parts, let's say x1 of t plus x sub 2 of t plus x sub 3 of t, let's say where x sub I of t is equal to capital A sub I cosine omega sub I of t, pass that x of t through a linear system, now you can write down what the output is, y of t. Y of t is just going to be the response due to each of those three separate sinusoids, and each of these y sub i's has exactly the same structure that we had before. We now have this a sub I, magnitude of h of j omega sub I, cosine omega sub I t plus the phase of h of j omega sub I. Now this might get a little tedious if we now had an x of t that had 5 or 6 different pieces that were sinusoidal, and we might get tired of continuing to iterate on that magnitude and phase calculation for each of those frequencies. And now maybe somebody says, oh, I'm going to give you a different input, and we'll learn subsequently that if we have a periodic waveform, now we can write that as some combination of an infinite number of sines and cosines. It might be nice to know what h and the magnitude and phase are for all frequencies. And that's why we want the Bode plot. If we can quickly find that, now we can immediately see what's going to happen to certain components if omega 1 is in the sweet spot or in the pass band of our h, and maybe omega sub 2 and omega sub 3 are way down on this cutoff region of our transfer function's magnitude, we can start to say, oh, roughly it's going to be whatever omega sub 1 provides in the output. That's all we'll have to worry about. And that's what we want to be able to do then. We want to be able to get this magnitude and phase information pretty quickly, and MATLAB can do that for us, but we also want to be able to check our work by sketching these maybe beforehand on the side of the paper so that we can check our work that MATLAB produces or provides for us. We can obtain the magnitude and the phase from these Bode plots. And it's plural because the Bode plots generically are two plots. We have the magnitude of h of j omega versus omega, where this magnitude is typically in dB for the Bode plot, and we have the angle of h of j omega versus omega. And these two sketches or plots allow us to better understand how this system, linear system H, is shaping or filtering signals that are applied to that system. And that's what this information will provide us. This will provide us a picture or a graph of what's going on for different frequencies. Let's just make sure that we're on the same page. I think we are, but let's look at an example. Suppose that I now do give you the analytical expression for that x of t that I put a minute ago in this figure. Maybe that's not clear what that is in terms of component parts or component frequencies, but it's actually cosine of t minus 2 cosine of 3t 1/2 cosine of 4t. Looking at this x of t, we can see that it has harmonic content. If I were to now play some instrument, the first harmonic is now oscillating at 1 radian per second. Pretty slow frequency. We wouldn't hear it. It'd be below what frequency if we can't hear it? 20 hertz, wouldn't it? So we may not be able to hear this particular x of t, but we could probably see it if it were, let's say, illuminating the intensity of some light. If this is the first harmonic, what's the next term? It's the second term, so what is it? It's 3 times the first, isn't it? So that's actually our third harmonic. The harmonic has an amplitude of 0, and the fourth harmonic has an amplitude of 1/2. Let's say that we're now applying that system, or I'm sorry, that input, x of t, to the following system, h of s. Which is now 1 over s squared plus 3s plus 1. Now, what if I say, what's the response, the sinusoidal steady state, due to the first harmonic? What do you have to do if I say, give me the component of the output resulting from applying this signal to this system, and I want to know the harmonic, the first harmonic in the output. First harmonic component, or how do we find it? All we have to do is use this system, don't we? This is some kind of filter or shaping. This is a linear system. We're now exciting this system with 3 different frequencies, the first harmonic, third harmonic, and fourth harmonic of this x of t. And right now I'm just asking you what's going to happen if we hit it with cosine of t, or what's going to be the response of the first harmonic. We can now identify omega sub 1 as 1. And that's now 2 pi f sub 1, or that's 2 pi over t sub 1 if we wanted to know how long is it going to take in terms of time, duration, for this to become periodic. So this takes over 6 seconds before it starts repeating itself. That's why it's such a slow or low frequency waveform. What we want to do now is figure out how the magnitude and angle are impacted by that particular system, linear system, H. And we can do that simply by evaluating analytically, if we want, replacing S with J1, or J omega, where omega is 1. This is now 1 over, we have J1 squared plus 3 times J1 plus 1. The J squared gives us a minus 1. We have a minus 1 plus 1, and we're left with 1 over J3. What's the angle of that linear system's transfer function at 1 radian per second? It's now the angle of 1 over J3, isn't it? What's the angle? And usually when we're doing angles, we talk about the angle of the numerator minus the angle of the denominator, if we wanted to. The angle of the numerator, 0, minus the angle of the denominator. That's 90 degrees, or pi over 2. So we now have this is producing a phase of minus 90 degrees at that frequency 1 radian per second, this system. What's the magnitude? I know it's pretty hard in this case. So now we take the magnitude of 1 over J3, and don't let J fool you. J has a magnitude of what? 1, doesn't it? We're just now 1 away from the origin in the S-plane when we go up J. And we've scaled that J by 1/3. The magnitude now is 1/3. If we wanted to know then what the first harmonic of the output response was going to be, we would have our original amplitude of our cosine omega t, or our cosine of t, which was 1. We would scale that by the magnitude of h at J1. We continue to oscillate at 1 in terms of radian per second. And then we shift it in time by this minus 90 degrees. And that's now the result of passing that waveform. So it does get attenuated a fair amount by that sort of innocent-looking linear system, h of s. The order of that system was what? What's the order of this h of s? Is it stable? Is it bounded input, bounded output stable? Well, here's a quick trick if you don't already know it. All you really have to do, if the leading coefficient has been normalized to 1, you really just have to look and see if these two coefficients are present and if they're positive. If they're both there, if they're present, and if they're both positive, you can immediately say those are going to have negative real parts. Whether they're complex or real, I don't care, but they're going to be in the left half S-plane. That transfer function is stable. If somebody now gives you an h of s that's 10th order, and they factored the denominator into 5 different quadratic terms, and each of those you can identify positive and present coefficients, you can now immediately conclude the stability of that 10th order system. Questions on that? What we want to do now is put together a process that allows us to sketch Bode plots almost like we sketched these fundamental waveforms in the time domain, these unit steps, these pulses, and ramps. We just started turning them on and turning them off at certain times. We want to be doing that in the frequency domain to sketch our Bode plots. And here's what I like to sort of keep in mind when we're doing Bode plots. I like to think of it as a 2-step process. The first thing that I like to do is factor. I get it in the right form and I identify my different pieces or parts that I want to now sketch. And then each of those parts individually sketch the straight line pieces that result from the magnitude and the phase information. where this h of j omega can easily be found if you've now found the transfer function in the S domain. By replacing S everywhere with j omega. What you will probably begin with is some generic or general transfer function. Let's say now you're given capital H of S is some b sub m s to the m plus b sub m minus 1 s to the m minus 1, and we keep going down to b sub 1 s plus b sub 0, all over a second polynomial. Let's keep a's as the coefficients there. A sub n s to the n plus a sub n minus 1. And in order to sketch this, or to get a feel for what's going on, it's nice to know where your roots are of the numerator and the denominator, or what are my zeros and what are my poles. If we were doing this in MATLAB, might call that denominator polynomial some den for denominator and just put in the appropriate coefficients in descending order. And if I'm missing a coefficient here on one of those S's, I need to make sure and include an explicit 0 in that location. Otherwise, I'm going to end up with a polynomial that's of less degree than what I actually have. In this case, I'm looking for Nevada roots of the denominator, or Nevada poles in this system. Once I've defined this as a polynomial, which MATLAB likes to play with vectors and matrices, now this polynomial is some vector. I can simply say P is equal to the roots of den. And that then provides me with the poles of H of S. Or if you don't have MATLAB fired up, or if you're somewhere and you now have your calculator, generally it's cleaner to use the complex zeros function because you don't know whether or not this polynomial is going to have all real roots or not. So let's just tell MATLAB we don't know, or I'm sorry, let's tell our calculator we don't know, give us the complex roots of this. If it was some fourth order polynomial, let's say it was now s to the fourth plus 2s cubed plus 5s squared plus 7s plus 35, for example, then we might say something like, well, S on the TI-89 is kind of buried on your front panel, and I like to just use X because that's a easily accessible key. You could then just say X raised to the fourth, or caret 4, plus 2X caret 3, plus 5X caret 2, plus 7x plus 35, and then you're telling it that x is your variable of interest, and that will then find the roots of that particular fourth order. And in fact, I've already done that, and I won't bore you with putting that in, but here is your x to the fourth plus 2x cubed, and where are the roots? How many roots do you expect? 4. The first one is a complex conjugate. It's basically at 1 plus and minus j2. But where is it in the complex plane? It's in the right half plane, isn't it? So that system is not stable. But the other pair is at -2 roughly, plus and minus j 1.8. It is in the left half plane. So is my system stable? No. All it takes is one unstable root or one unstable pole to cause the whole thing to be unstable. And here I have two unstable roots. Question? Okay, so maybe I didn't make that point very clear. So now I was specifically restricting. The question was, well, didn't you just say that the coefficients had to be present and positive and then you would have stable roots? That only works for a quadratic. Squared plus something, s plus something. Fourth order, third order, that's just a necessary condition, but it's not sufficient. Yes? So this is now telling the calculator, this is how this function works, is you've now entered in the polynomial, and now you're telling the calculator, I want you to evaluate for the values of x that cause that to become 0. So you're now saying, oh, that x that I've been sprinkling around in this expression, that's my unknown variable that I'm now trying to evaluate for in terms of where it forces that system to be, or that expression to vanish or to become 0. Where are the complex zeros relative to the value x? And those 4 are what we had now determined. They're sprinkled around the origin. 2 are in the right half plane and 2 are in the left half plane. And that system is not stable. Now we know where the poles are, and you could do the same thing for the zeros. Now we're ready to start factoring that fourth order, and maybe the numerator is third order, for example. What we want to do is get it out of, well, there are different ways of factoring a transfer function. The first one that's obvious is, now that we have the poles and the zeros, why don't we just explicitly write those down? I now have Michigan zeros, and I have Nevada pole factors. This particular form, because I can explicitly see where the poles and zeros are at just by the values of Z1, Z2, and the P1 and P2. Obviously, I'm now looking at what values of S cause each of these factors to vanish. And that will be my pole, or 0, depending on if I'm in the denominator or the numerator. And this is now called the pole 0 form. That's nice if you're sketching things in the complex S-plane. If you want to plot the poles and the zeros, this is the nice form to be in. Pole 0 form. If you're trying to sketch the pole and 0 locations and look at the distances and angles in the complex S-plane, that's a good structure to have it in. However, when we're doing Bode plots, having all of these P's and Z's by themselves messes things up in terms of the overall gain, and we'd have to redo the gain calculation all the time. To avoid that, what's nice to do for sketching the Bode plot is to force all of these constant coefficients to be 1, to factor all of those out. We need, for then the Bode plot, we need the time constant form. The other restriction that I will go ahead and tell you that we'll play with in this class is we are going to sketch these Bode plots for minimum phase systems. Have we defined what that means? Have we defined what a minimum phase system is or represents in this class? Made that comment yet? I can't remember if we have or have not. No? You don't remember me saying that? If a system is stable, where do you know the poles are? They're all in the left half plane, aren't they? A minimum phase system means that not only are all of your poles in the left half plane, but all of your zeros are there as well. A minimum phase system then says that all of the poles and zeros are in the left half complex S-plane. And that's what we will restrict our attention to in this class. We will always have our poles and zeros in the left half plane when we're sketching Bode plots. Just to make sure that we get this technique down. Once we've learned this, then it's pretty straightforward to look at things that are in the right half plane. If somebody says, oh, I have a non-minimum phase system, typically they're meaning they have a zero or zeros in the right half plane. How many people rode a bike today? Then you rode a non-minimum phase system. That has a zero in the right half plane, the dynamics of that bicycle. And that makes it a little more challenging to control or manipulate. But, yes, sir. Training wheels, that's a good question, but it may still be non-minimum phase. So if you came in on a tricycle, maybe a three-wheel mechanized machine, maybe that's minimum phase. Maybe a tricycle is minimum phase. I haven't really asked that question before. I always just, students would be content knowing that they were riding a non-minimum phase system. Yes? No, a non-minimum phase system typically means that if you wanted to go to the left, you start to go to the right first. Meaning if I commanded a system, let's say that I had some non-minimum phase system with a right half plane zero, and I said, I'm really wanting to approach that line, that's my command. The system may do something like that. It goes in the opposite direction initially before it comes back to where it's going. That's a characteristic of a zero in the right half plane. This is now the time, and this is, let's say, the output. For a zero in the right half plane. You don't need to know that. All you need to know is you have h of s and all of its zeros are in the left half plane and all of its poles are in the left half plane, and now we can start sketching it. To do that, if we've started now with finding the roots of the numerator and the denominator, what we want to do is first factor out all of those constants, which really means we're factoring out the poles, or let me just say factor out the pole or zero, in each of these terms, or what I will probably a lot of times call a factor. Meaning if I had a zero factor, that looked like the quantity s plus z sub I. What I'm really saying is let's pull that z sub I out, and I now have an s over z sub I plus 1, or I could now write that also as some z sub I times a t sub I, or s plus 1. That 1 over z sub I is the time constant. And this particular form, whether you keep the explicit zero identified or if you collapse it in and bury it into this time constant, this is then for one factor, it's now in time constant form. Let me see if we're all understanding this process by the following quiz. Here's a transfer function. H of s is equal to 10, s plus 10 over s times s plus 0.1, s plus 100 squared. Now, put that in time constant form. And make sure I can read your name when you don't hand this in. But I'm wanting to make sure that we're on the same page relative to pushing this into the time constant form that we need for a Bode plot sketch. For partial credit, you can write down the poles and the zeros. What good is a quiz if you don't hand it in? This is to try to get you guys active. What? You don't admit that, not now. So the comment was, I don't know what to do. Is that true for everyone? Trying to do, what's the form that it's in right now? Pole zero form. We want to put it into a form that explicitly puts a 1 here, it puts a 1 here, and it puts a 1 where that 100 is. So I'm going to have to factor all of those out. And I need to keep track of all of that as I'm doing it. That's what I want to do. I want to try to find the time constant form. Is everybody on the path to getting that? Are we ready to? I try to do it one at a time so I don't confuse myself. So the first thing I would probably do is just, in terms of thinking of this, I would probably say, well, let me just identify the poles and the zeros just so that I have my bearings. Do I have a finite zero? I have a finite value of s that causes that numerator to vanish, don't I? I have an s that's finite, that's bounded, that would allow that numerator factor to become 0. And that value of s, I just plug s plus 10 and set it equal to 0, and I find s is equal to minus 10. That's pretty easy, right? So I do have a 0. Do I have any other finite zeros? What's the order of this system? What's the order of this system? And how much of that transfer function do I need to show you? Could I have gone ahead and scrolled up? As long as you know the numerator is strictly less, that would be a strictly proper transfer function. As long as the numerator order is strictly less than the denominator, that's a strictly proper transfer function. Is it third order or is it some other order? How many think it's third order? How many think it's fourth order? Okay, we can't forget that 2 up there that's squaring that one factor. So we have a fourth order. We should be expecting 4 finite zeros. We have 1 0 right at the origin. That will cause the denominator to vanish. We have another we have another root of the denominator, which is a pole. One of our poles is at the origin. We have another pole at minus 1/10. That's pretty close to the origin, isn't it? Relative to these other 2. And that's now our pole 0. Can you visualize that pole 0 pattern in the complex S-plane? I'm sorry. So I should have a 0, a pole at the origin, a pole at minus 0.1, a pole at minus 100, and a pole at minus 100. Yes? Is this system minimum phase or not? It's a good question. We are going to allow this to be minimum phase. As long as it is on the imaginary axis, that's okay. So this is okay. We'll call this a minimum phase. We're going to be able to treat these poles, or if we had a 0 at the origin, we'll learn how to sketch those. But anything in the right half plane, we're going to keep away from. If it exists on the imaginary axis, we can still sketch it. But what we're going to do is we're actually going to, here's your visual. If we had a pole on the imaginary axis, we're actually going to rotate it around and stay the same radial distance away from the origin and make it purely real, just to simplify our sketching. But we'll talk about that in a minute. Now we have our poles and zeros. Meaning we can now look at factoring this guy into the time constant form. Upstairs we started with a 10, but we then also factored down a 10 for that 0, and we had s over 10 plus 1. Downstairs we had a pole at the origin, then we had a pole at 0.1 negative, so we'll factor that out. And if it's confusing, then I would just break that quadratic or that squared term into 2 parts and say, okay, one part I'd factor out the 100, and then I have another one that I'm going to factor out the same way. So the minuses occur because I'm setting those factors equal to 0, right? And those, I haven't changed any pole or 0 location in this form, have I? If I now set this factor, this s over 0.1 plus 1 equal to 0, I'm still going to get the value of s equal to minus 0.1 that causes that to vanish. I simply need to collect or consolidate all of my constants, and then I'll have it in time constant form. Meaning, what if I now, what do I want to do? Well, I can clean this up. I can say that cancels one of those, and this 10 cancels that 10, and this 10 cancels one of those. Now I just have 1 over 10 as my gain, meaning I now have h of s equaling 1 over 10, or 0.1, s over 10 plus 1 over s over 0.1 plus 1, s over 100 plus 1, but I have that twice, so I'll just put it that way. And this is now in time constant form. Is that what you were getting when you were doing your time constant form before? Now we can sketch this. And what kind of terms do we have? We have a factor that's just a constant, so we need to learn how to sketch the Bode plot of a constant. Well, that could be a positive or negative number if I really wanted to make it complicated. But that would be a constant. We have a term like this. This is called a linear factor. It's just an s to the 1. So we have to learn how to sketch linear factors, either upstairs, 0 factors, or pole factors. We could actually have complex roots, and that would give us a quadratic factor. And we need to learn how to sketch quadratic factors, and I'm going to provide you with an oversimplification of how to sketch those. It's not what it really does, but it allows us to quickly sketch with straight lines what's going on in the limits. And we also need to figure out how to plot the Bode plots for poles or zeros at the origin. Those are all we have to do. And what I'm going to really do is I'm going to collapse these quadratics into terms like this that look like 2 linear factors at the same location. So all you have to learn for this class is how to sketch constants, linear factors, and poles and zeros at the origin, and put them all together. Clear? Now, some ideas that we'll start going over is, well, let's not get ahead of ourselves. Now what we want to do is identify the individual terms, which I just did. So let's now start with these individual terms. We have 1, which was a constant, and maybe we just say, oh, let's just say that we have some constant h sub 1 of s equal to some number k. And let's learn how to sketch that. Magnitude versus frequency and angle versus frequency. We also want to be able to sketch poles or zeros at the origin. So we could have just an S, which I've indicated here in the middle, Or maybe we have 1 over s squared. Or maybe we have 1 over s. Now in the time domain, what's 1 over s looking like as far as an operator? When somebody said, oh, you know what? I have a system that has 1 pole at the origin. What are they talking about? It's just an integrator. They have a pure integrator. So now think of, if somebody says an integrator, do you remember your op-amp circuit to realize an integrator? You have this resistor and then a feedback path which includes a capacitor. That's now an integrator, where that feedback path is going back to the inverting input of your op-amp. This then, in the frequency domain, this 1 over s, in the time domain is really just an integrator. So if you put in a signal to a system and integrated it, and out pops its result after integration, the system behavior in the frequency domain would just be this 1 over s. And we want to figure out how to plot that as far as its Bode plot. If this is an integration in the time domain, what is a 0 at the origin? A differentiation. And we'll learn that that looks like something like this in terms of its magnitude behavior in the frequency domain. What else do we have? We also have linear factors. And now I'm just emphasizing that that pole located at minus omega sub b is a frequency. I'm labeling it as an omega sub b. It has some bandwidth. This now is what kind of a behavior? If somebody gave you this transfer function and they said, what is that system doing? What would you tell them? It's a low-pass filter, isn't it? What's the DC gain of that system? 1. So it's going to be flat out until it hits this pole or this break frequency, and then it's going to go down. You know what a low-pass filter looks like. So now you can sort of anticipate what you're going to be sketching in terms of the magnitude behavior of that h sub 3 if you just had one linear factor. The next term or factor that we will simplify is a complex factor or factors. Let me just say, let's suppose that we have a complex pole factor, s squared plus 2 zeta omega sub n s plus omega sub n squared. And now we're just introducing some new notation so you can go home and impress your friends. And when you're eating dinner tonight or something, you can just start saying, here's a complex factor. Let me show you where that is in the complex plane. Right? And it's a function of zeta and omega sub n. Omega sub n is the natural frequency. And that's actually the distance those poles are from the origin. If we now sketch that factor, or those two factors in the complex S plane, let me see if I can sort of sketch this. That's supposed to be a semicircle. Here is the imaginary axis. Here's the real axis. This is the complex S plane. And let's suppose that the pole ends up being there. And those are now complex conjugates of each other. This particular distance is now, this point is minus sigma, so this length is sigma. This is now minus sigma. Or that's now this zeta omega sub n. This distance is now our damped frequency, omega sub d, which is then at a location of j omega sub d. So this is now j, and this is related to the natural frequency, omega sub n, by this scaling factor, square root of 1 minus zeta squared. That's the relationship between these sigmas, omega sub n's, omega sub d's, and zeta. This particular distance is the natural frequency. And a lot of times we will, if you were taking a controls class, you might be interested in that angle theta that this pole is making with this negative real axis. Now, as we vary zeta, do you see how this pole will slide around that half circle? If we let zeta go all the way to 0, where's that set of poles going to be living? If zeta is 0, this real part is going to shrink in here, isn't it? And we're going to be right on the imaginary axis. And our damped frequency will be the same as our natural frequency. When we get to this point right here, zeta equals 0. At this point is zeta equals to 1. And all of these are related to what we've already been talking about. We've talked about poles at s plus sigma minus j omega sub d. And where is that pole factor going to, where's the s that causes this factor to vanish in the complex S plane? First quadrant, second quadrant, third quadrant, or fourth quadrant? Where is this one? Remind me again of my quadrants. Is this first, second, third, fourth? Where is this term? Second, isn't it? It's up because this S equal to minus sigma plus j omega sub d will cause this to vanish. This is associated with the pole in quadrant 2. Then its twin downstairs is given by that factor. This is the root in quadrant 3. If we now multiply those out, we have s plus sigma squared. And do you see that the cross terms cancel? We have a minus j omega sub d times s plus sigma plus j omega sub d times s plus sigma, and we only have the minus j squared omega sub d squared. The j squared is a minus 1. It cancels the minus, and we end up with plus omega sub d squared. Well, if we multiply this out, this is now s squared plus 2 sigma s plus sigma squared plus omega sub d squared. But that, we said, was the same as this other factorization, which was s squared plus 2 zeta omega sub n s plus omega sub n squared. And this is now how you can relate those two factorization forms of a complex factor relative to if somebody says the natural frequency in zeta, or if they say the real part sigma and the imaginary part, the damped frequency omega sub d, you now know how they're related. The natural frequency omega sub n is just this hypotenuse of a right triangle with one side equal to sigma, the other side equal to omega sub d. So you have a squared plus b squared is c squared. That's your natural frequency. That's the distance you are away from the origin. And if you compare the coefficients that are scaling the linear factor in S, the 2's are the same, and sigma is just zeta omega sub n, and that's the distance into the left half plane that that root is located, zeta omega sub n or sigma. Questions on that? Here's what we're going to do. When we're sketching transfer function Bode plots, you may come up with poles that are right here, or zeros that are somewhere that are complex conjugates. What I'm suggesting that we do, so that we're all playing the same game, we just agree for sketching purposes. It's not what actually happens, so don't think that MATLAB should be giving you what you just sketched. You're doing an approximation, but you're getting something that in the limits is behaving like what the real system will do. We are going to go ahead and let zeta be 1. We'll just slide these two so that we now get 2 real roots instead of 2 complex conjugate roots. And then we'll just sketch real roots, and we'll have 2 real factors to sketch instead of having to worry about 1 complex pole pair or 1 complex zero pair. Is that clear? Yes. No, what we're doing is we are actually approximating the behavior that will happen, and maybe I'll show you, I don't know how much time we will have. We'll do this near the end of these different linear or these different individual term sketches. But you'll see what happens when we have a linear factor. Then we'll let that go to the extreme and say, well, what happens if we had purely imaginary poles? So let's just do that now for the magnitude. If we now had purely imaginary poles, and that's all we had, were 2 poles on the imaginary axis. Let's say that we had a pole at J1 and another one at minus J1. We have the 2 poles sketched. What does that do with the big top tent or the circus tent? Those are infinitely tall poles, aren't they? And we stretch a rubber sheet on top of that, wherever those poles are. What does that mean? Well, as we're walking up this path, the magnitude, the height of that tent is getting bigger and bigger until we get right on top of that pole, and then what happens? The height goes to infinity. And then as we walk past that, it starts to come down. So in terms of a sketch, we have something that would just go whoop and then come down in terms of its behavior if it was a pole. This is now just its frequency response behavior, which says that if you now, what does that mean? If you have 2 poles at J1, is that a bounded input, bounded output system? If it's not, what input waveform could you apply to that system to cause an unbounded response? You could hit it with 1 radian per second, couldn't you? And then you would just go unbounded. No, it doesn't matter really. If you have poles at the origin, or I'm sorry, on the imaginary axis, if you have poles on the imaginary axis, now if you excite those at that frequency, you're going to have an unbounded response as a function of time. That's all I'm saying. So now if this can had 2 poles on the imaginary axis, and I shook it at that same frequency, then its output response is going to go unbounded. And you don't want to see a trash can blow up, do you? So we won't inject that particular frequency. We'll be a little bit off its natural frequency. Yes, sir. There will be another review before the next test, and I now need to figure out when that's going to be. But let's see if we can at least sketch some of these before we run out of time today, as far as these different terms. What's happening if we sketched a constant term? And I think Goldilocks might have to wait until Thursday. So you'll have to wait and come back and hear the Goldilocks story on Thursday. I know, you won't be able to sleep for the next 2 nights in anticipation. It's not quite Oz, whatever that show is. It seems to be getting advertised everywhere, but it's Goldilocks. Constant. Let's say our transfer function h sub 1 of s is k. What happens to that in terms of its frequency response? He's saying, let's walk along the imaginary axis. Let's replace s with j omega. That's just k still. If we now compute its magnitude in dB, that's just 20 times the log of whatever k was. And really, I guess, to be more thorough, let me just say it's base 10 log, and it's the magnitude of k, and that's true for all frequencies. It's just a fixed number. If k was 1, what would the magnitude in dB be equal to? 0. If k was 10, if you now had in the actual system a gain of 10, what would that look like in dB? It's 20 dB. If you now had a gain of 100, then it's 40 dB, isn't it? If you had a gain of 1,000, it's 60 dB. So now you would have a straight line, a flat line, at that particular dB level. If k was 1/10, which it was in our example, what is the magnitude in dB? Now you've already told me what the log of 10 was, didn't you? Log of 10 was 1, so the log of 0.1 is minus 20 dB for all frequencies. And if you had to sketch that, this is omega, and this is the magnitude of h sub 1 in dB. You're now down below, if this is now your 0 dB line. Now, what's the phase of h sub 1 of j omega? That's going to be 0 if that gain is positive or non-negative. Or let's just agree that it will be negative 180. It could be plus 180, and MATLAB may sometimes give you plus 180 if you had a negative gain. And it's that angle for all omega. We've done one of the terms. We'll have to come back and listen to Goldilocks on Thursday and figure out where that fits in with Bode plots.